Hello, this is another lecture for material science subject. So this is module 4, lesson 2. In this topic, we will talk about mechanism to strengthen metallic materials. So in the previous lesson, we talked about plastic deformation and how motion of dislocation influence plastic deformation. And today we are going to talk about how, if we hinder the movement of dislocation, we can strengthen metallic materials. So let's get started. One of the learning outcomes for this lesson is by the end of this topic, you should be able to explain how grain boundaries impede dislocation motion. You should be able to describe and explain solid solution and precipitation hardening and their interaction with dislocation, and also how they will impede dislocation motion. And also, you should be able to explain the phenomenon of strain hardening or cold working. So from the previous video, from topic of plastic deformation and dislocation motion, we have now understand that the ability of a metal to be deformed is totally depending on the ability of dislocation, which is line defect, to move on a slip plane. Therefore, if we can restrict this dislocation motion, metal can get stronger. So all measure with the aim of blocking the dislocation from moving are summarized under this topic and under the term of strengthening mechanism. So there are 4 mechanisms to strengthen metallic materials. And the first one is by grain boundary strengthening, solid solution strengthening, strain hardening, which also known as cold working, and also by precipitation hardening. So in this lesson, we will talk about all these 4 strengthening mechanisms. And I will start with grain boundary strengthening. So from previous lectures, we already talked about polycrystalline materials. So polycrystalline material is a materials that consists of a numbers of grain inside its microstructure. So as an example, this image microstructure here has a few grains forming the whole volume of this metal. So the surface where the two grain meet is what we call as grain boundaries. So grain boundaries, we classify them as 2D defects in a crystal structure. If we look at a simple schematic of grain boundaries, the atoms in each grain has different orientation. They form the same crystal structure, but because during solidification, when they start to solidify, they're forming grains with different orientation. So if we have, let's say, dislocation in one, and we have this as a slip plane for this grain. And for this grain here, we have this as a slip plane. So dislocation will move through this plane here and here as well. Because of the different orientation between the grain 1 and grain 2 here, dislocation cannot simply jump when they reach the grain boundary. So among other things, grain boundary disrupt the motion of dislocation through materials. So during deformation, dislocation motion will be impeded at the grain boundary. So as you can see in this schematic here, when shear stress is applied to these materials, this edge dislocation will try to move. So this dislocation will move to that direction. And as soon as it reaches the grain boundary, it will stop there because the slip plane at this grain 2 here do not line up with the slip plane at grain 1. So because the slip plane in one grain do not line up with the slip plane of the neighboring grains, this dislocation will be impeded at that grain boundary. And since the two grains are of different orientation, dislocation passing into grain 1 will have to change its direction of motion. So this will become difficult for this edge location to change its direction. So if we talk about a lot of dislocation on that slip plane there, the grain boundary will block the first dislocation and the other dislocation will pile up behind it. And this will create tension in this region here. So this tension that was built by the piling up of the dislocation will create or build a driving force for slip activation in the neighboring grain. So a material with larger grain size will be able to have more dislocation pile up, and this will lead to a bigger driving force for dislocation to move from one grain to another grain. You will have to only apply less force to move the dislocations. So with that logic, if we can decrease the grain size, we can also decrease the number of pile up at the grain boundary. So if you look at the schematic here, if we have a larger grain, we will have a lot more dislocations. And when we apply shear stress, when deformation happens, they will all going to move to the grain boundary, and there will, because of the misorientation between the two grain, they will all going to pile up in this region. And they will build or create a tension in that region and also will build the driving force. So the larger the grain size, the higher the driving force, because a lot more dislocation has been piled up in this region. And you will only need a smaller applied stress to actually move them to the neighboring or across the grain boundary. But when we have a smaller size, we also going to have a smaller dislocation. So when deformation happens, only a small number of piling up of the dislocation will happen in this region. So a smaller driving force. So we will need to apply a higher applied stress to move dislocation across the grain boundary. So the higher the applied stress needed to move the dislocation means we are now creating a material with a higher yield strength. So how do we create, or how do we get a material with a smaller grain size? So during solidification, we can put grain refiner. So the more grain refiner inside the materials, what will happen is the more nuclei will form in the materials, and a lot more grain can form simultaneously. So that's one way. Another way is we can supercool the materials to a very, very low temperature, much lower than the solidification temperature. So at that, when we supercool them at lower temperature, a lot more nucleus can be formed. So there will be a rapid formation of nucleus. So a lot more grain will start to grow simultaneously, and eventually they will impede each other and create a lot of grain boundary. So another way is for a solid metal, we can heat treat them, which we will learn in the next lesson. We can heat treat them, we can do co-working, and then we can heat treat them to create a smaller grain size. So a smaller grain size means a lot more grain boundaries. So you will strengthen the material using this grain boundary mechanism, strengthening mechanism. So the second mechanism to strengthen metallic material is through solid solution strengthening. So solid solution strengthening is a method of improving the strength of pure metal using alloying element or impurity atom. So the principle of solid solution hardening is based on the distortion of lattice by foreign atoms. So impurity atoms will cause non-uniformity in the lattice, and it will make plastic deformation more difficult by impeding dislocation motion through the stress fields created by the impurity atom. So due to their blocking of the dislocation movement, the lattice planes can consequently no longer slide off easily. So the deformation of lattice occur only at significantly high shear stresses, since the lattice distortion must be overcome. So there are two ways for alloying element can be introduced into pure metal. Is one by solid solution, substitutional solid solution, and the other one by interstitial solid solution. So in the case where impurity atoms are small enough and they are able to fit into spaces between the host atoms, we call them as interstitial solid solution strengthening. So in this case, the impurity will catch the dislocation and prevent it from moving further. So if we look at this schematic, this is our dislocation line, and it will glide on this plane here. So yesterday, from the previous video, we defined slip plane as the closed dense plane, and the direction where the dislocation will move is where the atoms touch each other. So if this plane consists of all the same atoms, this dislocation line will just glide easily. But now we have one impurity atom. So this plane will be distorted. So it will take a lot more effort for this dislocation to glide on this slip plane. So when we need a lot more stress to move the dislocation, means that the deformation only can happen at a higher stress. So we have created a material with a higher yield strength. So in the case where impurity atoms replace the host material in the crystal lattice, as of this schematic, we call this strengthening mechanism as substitutional solid solution strengthening. So due to the variation of size between the two atoms, they also will create lattice distortion. So when there's irregularity on the slip plane, the dislocation cannot easily move around this interruption. So again, a higher force will need to be applied to this material for that dislocation to move, for the deformation to happen to these materials. So when we need a higher applied stress, means that the material has a higher yield strength. Another method to strengthen metallic material is through a mechanism that we call as precipitation hardening. So through precipitation hardening, we introduce particles or precipitates instead of foreign atoms. So these particles will block the movement of dislocation. So in this microstructure here, this is a microstructure of high strength low alloy steel. And you can see in this microstructure, there's a small particles distributed uniformly. And these particles is small particles of titanium nitride. So these particles will now act to block the movement of dislocations. So the higher strength, a higher stress will need to be applied to these materials in order for the dislocation line to move on the slip plane. So uniformly dispersed particle within a metal grain will help hinder motion of dislocation. And this subsequently will increase the strength of the material. And the last mechanism that we're going to discuss in this lecture to strengthen metallic material is strain hardening or cold working. So to explain strain hardening phenomenon, I will need this metal again. All right, so if you try to bend this metal and then unload it, and if you try to bend it again, unbend it, you will actually require a lot more force. And try to do it again at the same location, you will need a lot more force again. So the same, you keep doing it. These materials actually, as every time you bend, you load and unload them, it is becoming harder and harder. So I would like you to try it yourself. Use a paper clip and try to bend and rebend and unbend, load and unload it, and you will see what I meant. It is actually you need a higher force each time to bend them. So this is because as we have bent them, we introduce plastic deformation. So when we bend them, this material has experienced plastic deformation. So during this process of plastic deformation, we have introduced a lot more dislocation. So we created a lot more dislocation inside this area of that materials. So when there's a lot more dislocation, and we know that dislocation is interacting with each other. So the principle of strain hardening or cold working is based on the introduction of additional dislocation during plastic deformation. So during this plastic deformation, materials become harder and stronger as it's plastically deformed. And in every deformation process, new dislocation are always going to be introduced into the metal, so into the materials. The dislocation will hinder each other from moving. So it's just like our hair as well. If we have a lot more tangled with each other, what we need to strengthen them back is we need a lot more force. So when we have a lot more dislocation, it will interact and tangle with each other. So we will need a lot more force to actually move them. So when a metal is plastically deformed, dislocation move and additional dislocation are generated. So the more dislocation within the material, the more they will interact and they become pin and tangle with each other. So another way to explain strain hardening phenomenon is through tensile tests. So I have this metal here and I am performing a tensile test to it, and it breaks at this region here, and this is the tensile strength of these materials. So it fracture at that point there. So what happened during tensile test is this material will stretch until it reaches its elastic limit. Plastic deformation will happen. And we have explained in the previous slide that work hardening or strain hardening is a consequences of plastic deformation, a permanent change in shape. So if, let's say, when I did this test now, after it reached its limit of elastic limit, I am going to now just introduce a little bit of plastic deformation. I'm not going to break them. Instead, I will unload them. So I will unload them at 0.3 here. And then I will do this test again. One more time, I will start this test again. Since elastic modulus of materials is the inherent or intrinsic properties of these materials, this slope will not change. So when I do the test again to the same sample, what will happen is the yield strength now will move to this point. So the materials will now experience plastic deformation at this point here. And it will continue. If I break it, if I test it until it breaks, it will break at the same point. But what I did, because of the first plastic deformation I have introduced during the first test, this material has increased in yield strength. Because what happened here is a lot more dislocation has been introduced. And previously inside that material, there already exists also dislocation line. So now a lot more dislocation line are interacting and tangled with each other. So during the second test, for me to begin plastic deformation again, I require a lot more force. So, and if, let's say, I did not break them, I unload them at this point. So I unload this at that point and I retest them again. So if I retest the same sample again, what will happen is, remember the Young's modulus is not going to change, so this slope is going to be the same. So now the plastic deformation will happen at this point. So you can see the same sample now having a higher strength, a higher yield strength, because during the second test, I introduced a lot more dislocation at that point. So when they become tangled with each other, you need a lot more force to move them. But you can also see what happened to this material because it is going to break at the same point. The ductility of this material will be reduced. So using this strengthening mechanism, the material strength, yield strength will increase. However, its ductility will reduce. So we can calculate the percentage of co-working using this equation, but we're not going to discuss this in the video because I found that the easiest way to discuss co-working percentage is through tutorial. We're going to solve some problem related to co-working percentage, and from there you can see how with different percentage of co-working material can increase in its yield strength. So in summary, through this lecture, we have learned the 4 various mechanisms involved in strengthening the material. So we can use different mechanisms to strengthen materials by impeding the dislocation motion. So by decreasing the size of grain in polycrystalline material, the yield strength of the material can be increased. So by introduction, a lot more grain boundary, we can increase the strength of materials. The addition of impurity atoms or precipitate can also impede dislocation motion, and subsequently this will increase the strength of the material. Co-working can also introduce dislocation in material and cause them to tangle and interact with each other. And subsequently, with this mechanism, the strength of the material can also be increased. So that's about it for this lecture. Thank you for your attention, and I will see you again in the next class. Thank you very much.